Thank you so much, everybody, for joining this panel discussion on climate change, machine learning, and the power grid. I'm super excited about just this awesome slate of speakers we have lined up. Yeah, looking forward to learning a lot today. Just to give a little bit of an overview on the attendees here. So we actually have attendees from all 6 continents and about 50 countries, which is really exciting. We hope that while this webinar is sort of one start to learning about these topics, that this is, just an initial touch point that you'll sort of continue to engage and reach out to each other, et cetera, because these kinds of course, like multinational, like global collaborations are exactly the kinds of things we need to tackle climate change and address some of the biggest challenges that we have in the power sector. So just to give an overview of what today will look like. So we'll start with a talk from Antoine Moreau from RTE, followed by some Q&A. And then we'll sort of, after that, we'll get to 3 talks from Kyri Baker, Eric Xie, Caitlin Albertoli, and Vic Chowdhury. And so we'll have those 3 talks in sequence before then going to a panel discussion and Q&A with the last 3 speakers. So throughout the talks, feel free to ask questions via the Zoom chat, and we will try to get to as many of them as possible. I'm anticipating there will be a lot, because again, these are going to be awesome talks. So before we dive in, just wanting to give a brief overview on the 2 organizations who are hosting this event, so Climate Change AI and the Energy Innovation Network. So Climate Change AI is a volunteer initiative that looks to build a community of people working at the intersection of climate change and machine learning. So we have, for example, a virtual workshop coming up in December, where there'll be presentations of various work going on in this area and opportunities to meet people. We also have things like tutorials on our website. We wrote a pretty large paper called Tackling Climate Change with Machine Learning that details applications of machine learning to tackling climate change, as the name might suggest. And so a number of people in the registration sort of asked the question of how in general can machine learning help tackle climate change? While today we're sort of going to hone in on specific applications in the power sector. If you're interested in a broader view of that topic, I would definitely encourage you to check out our website, which is just climatechange.ai, where you can find the paper, tutorials, and also an interactive summary of the paper that is a little less monstrous to go through than the full paper itself. So this is sort of what's covered in the paper, basically different applications of machine learning to areas like power systems, which we'll discuss today, but also things like buildings and cities, transportation, societal adaptation, industry, climate science, and much more. So again, if you're interested in sort of understanding the broad landscape of how machine learning fits into climate action, I would definitely encourage you to check this out. As I mentioned, we'll be holding a workshop in December with a couple of keynote speakers who are drawn from, academia, policy, the startup sector, etc. So should hopefully give kind of a broad perspective on the different ways in which you can pursue climate action, no matter sort of where you're coming from. And we'll have panels and posters, etc. This event is, of course, virtual, though the picture on the slide is from our physical event last year. We also have a discussion forum, so the URL is at the top. And this forum is a really good place to meet other people who are working on this topic. There are lots of discussions about, for example, interesting papers that are being shared, or people pitching their startup ideas, or sharing their journey as to how they got into this area, or looking for co-founders. So I definitely encourage you to join into the forum if you're interested in basically following up on the topics that you're hearing about today and meeting other people who are working in these areas. And then finally, we also have a monthly newsletter where we share things like calls for funding, or calls for proposals, funding, project readings, jobs, et cetera, et cetera. So you should have been prompted when you signed up for this event as to whether you want to sign up for the newsletter. We'll add everybody who said yes later this week, but you can also check out past issues of our newsletter online and sign up if you would like to, and you had sort of opted out. So that's the climate change AI overview, and I'm going to hand it over to Na to talk a little bit about the Energy Innovation Network.
Great. Yeah, thank you, Priya. Hi, everyone. My name is Na Yu. I'm a data and analytics consultant at Slalom Consulting based in San Francisco. And also I'm the vice president of Energy Innovation Network. First of all, just want to say it's a great pleasure to co-host this event with Climate Change AI. And very excited to have our wonderful panelists today. And thanks for all of the audience participation today as well. So Energy Innovation Network is a nonprofit organization, volunteer-based. We were founded at Stanford in 2015. Our vision is to really provide a platform to bring professionals together to strengthen the exchange of technology, development, research, and the businesses as well as policy in 3 areas: low carbon energy, transportation, and the environment. We are currently headquartered in Silicon Valley, California. We have about 20 core members crossing the world, like Silicon Valley, Colorado, Shanghai, and India, and Nigeria as well. Next slide, please. So throughout the year, we host the various events. For example, in the past September, we just hosted a Inspire Summit, where it's a TED Talk style conference. We had the 11 enablers from the world, from 8 countries, to share their innovations in sustainabilities. And actually, I also met Priya through that summit as well. We also had one of the speakers join EIN as well. And other events, for example, we had the investor and startup mixture, where we invite entrepreneurs from energy industries to share their business ideas. We also have an education program to provide online courses surrounding energy and sustainability. And we keep recruiting committee members. So if you are interested, please feel free to reach out to us. Next slide, please. So I also would like to share one of our upcoming online education program. It's about renewable energy and renewable energy finance course. So our instructors are Professor Daniel Kamen and Professor Steve Weisman from UC Berkeley, as well as Bill Wang, President of Amergy Solar. The course will be really focusing on about the overview of the renewable energy landscape and also how the renewable energy finance work. The course will be provided in February 2021, and the registration will be open in December. So if you are interested, please look out for that. That's all. Thank you, Priya, and now back to you.
All right, thank you. And so with that, excited to sort of dive in to our program here. So Antoine, if you want to share your screen. So in the meantime, I'm just gonna read a little bit about Antoine here. So Antoine Moreau is the lead AI scientist at RTE, the French transmission system operator. He holds a double master's degree in engineering from the École Centrale Paris and Stanford University. After interning at Tesla Motors, he joined RTE R&D on the Apogee project 6 years ago with the long-term goal of developing a personal assistant for control room operators with AI. He is also one of the people running the Learning to Run a Power Network Challenge running alongside NERVS 2020. And this is a strong step forward towards his vision of building a new AI for power systems community. So with that, Antoine, thank you so much for joining us, and please feel free to take it away.
Yeah, thank you, Priya. Thanks a lot for the invitation. I'm very pleased to be here to talk about this great cause challenge about climate change. I think it's something we all have to tackle, and power grids have something to say there. So yeah, let me give you this presentation about empowering smart grids with AI in the 21st century. And let me start with this phrase from Andrew Ng. So probably many of you already know him. He's a famous professor at Stanford in artificial intelligence. And so he had this phrase, artificial intelligence is a new electricity. So obviously it talks about electricity, so I like it. But I mean, you should not take it in the literal sense. What he meant is that electricity in the past century was clearly a revolution for the society, you know, at every layer. Everything changed thanks to electricity. And possibly artificial intelligence could have the same impact in the 21st century. But it remains to be seen. So, and there you can wonder, is electricity basically already a soft challenge from the 20th century? And will AI be the 21st century achievement? And from there, for the first question, then this leads to, are blackouts basically a story of the past? And hopefully, I hope that not many of you experience blackouts today, but actually it's still the case. And in Europe, for instance, we had the big events in 2006. So you can watch this very nice video from a German university explaining all the events and how bad it went. But it didn't go down, so not an entire blackout. But nowadays, you might have heard for the last years, in New York, in California, in London, you had some events with blackouts. And if you want to get a sense of how much it costs, you know, to society, there's this nice simulator from the European Commission. So it's not perfectly accurate for sure, right? But it gives you a sense of how much it costs. And for instance, if you select the region of Paris, and you ask, okay, what will cost a blackout today at 8 a.m. for an hour? Basically, you get this answer. So it's around 100 million. So that's a lot, definitely, and not something we like to see. So are blackouts a story of the past? The answer is not really. But we still like, you know, electricity to be a common good, for sure. At the same time, we have this other system to consider, Earth. So we all know about climate change today. And what we'd like to do on the grid is to use less fossil fuels to generate, to produce electricity, and also limit the grid expansion to reduce the grid footprint. At the same time, we like more renewables on the grid and to use more flexibility, possibly with AI. So that's the question. But here, basically, sustainability is really the key, and future smart grids, they will have to do better with less. And not to forget, you know, the current pandemic, which adds a lot of uncertainties and challenges to operate a power grid. So question now is, okay, so blackouts are not really a story of the past, but so how can AI be of any help here? And what we like as power grid operators is to assist our human operators. And I usually give this quiz to people that are not very familiar with energy, so I guess this is very easy for you. But you can wonder, okay, how much time on average a grid could run without human intervention? And the answer, you know, is not forever. The grid doesn't run by itself magically today. There's still a lot going on behind. And for sure, storms can be very impactful, can damage a grid. But basically, if you do nothing already in an hour on average, you lose the grid. And it can go a lot faster sometimes. And hopefully we have some automating to help us with those dynamics, fast dynamics, most often. So yeah, basically, at least every hour, you still have a lot of human decisions to operate the grid today. And when you look at the working environments of those human operators today, so the control rooms, those are quite crowded work environments where you see many applications and screens, lots of information. So that's starting to be quite difficult, quite complex to manage a grid, this kind of work environment. Not to forget that the complexity is rising because we want more renewables that are distributed over the grid. We might have some prosumers tomorrow, some new actors in the grid. And in Europe, we're also widening the grid. So basically, we have electricity flowing all across Europe now. So that's many actors and new scales to handle. At the same time, the nature of the grid is kind of changing. You have some new technologies and some hybridization of the grid. And we cannot build new lines as we did in the past. So we don't have a lot of margin. So definitely we need to be very smart with the flexibilities, and hopefully digitalization and AI can help. But yeah, today if you go back to see your operator and say, okay, we have this new cool application, is that okay with you if we come with a new screen? Basically, I mean, he will say no. He has too much to manage, like it is today. But at the same time, we have to consider that definitely humans will remain key players to operate the power grids, because those are very critical systems. There's a lot of responsibility and transparency to operate a grid for the common good. So definitely they will still be there. And the question is, okay, how can we rethink basically this whole ecosystem, the human-machine interface? And we have a project for that, which is called Apogee, where we want to design a new assistant for control room operators. And basically to move from a supervision mode where you have a lot of fragmented information over every application to an hypervision mode where we refocus them on their task rather than having them monitor alarms. And for every task, we try to give them the relevant context and some suggestions. And our company, actually, since it's a public service, we have a lot of incentive to open source everything. So our code, our data, and to organize also some challenges, competition so that other startups or utilities can bring some new solutions to us. So you can check that out. The Linux Foundation initiative for energy has been there for 3 years now. If you like to see what's going on the grid, you have this nice application, Eco2Mix, to check out as well. And also what we noticed, is that we have the power system community on one side, we have the AI community on the other side. Those are two very rich communities with a lot of smart people and a lot of different approaches. But the bad thing is that they're not talking that much to each other, while we believe there will be great synergies between those two communities to move forward. So we wanted also to onboard the larger research community to work on a power grid related problems and to basically break this wall. And that's why we launched this challenge, Learning to Run a Power Network challenge, to test the potential of AI to help us robustly operate the power grid. So you can see here a small example of a power grid running over time. So you have productions and consumption evolving through time. And then you see the flows over the grid that are changing as well. And some lines are getting close to their physical capacity. And after that, if you have an overloaded line for some time, just disconnect, because we want to protect the grid. And then the bad thing is that you might have a cascading failure after that, because other lines get overloaded as well and they disconnect, and then you lose the grid. So basically we want to avoid this kind of situations that can lead to a blackout. And L2RPM is today a series of competitions. So we started small last year with a small grid and mainly no real events. It was representative of the winter months. And this year we scaled up the problem. So we had some events like maintenance, but also some adversarial attacks on the grid. So you could have some line disconnected by a hacker, for instance, or just lightnings on the lines. and a lot more actions to handle. And also we wanted to test the adaptability of those agents, so those artificial agents that were submitted to those competitions. So when you increase the mix of renewables, are you still able with the same models, the same AI, to actually manage all those energy mix? So that was quite dynamic and interesting. The winning team actually all come from China this year, so that's very impressive. But we encourage you to check that out as well. You can still submit your own solutions as a benchmark. So that's a thing of interest to you. And as well, you can inspect the winning solutions through those scenarios on which we tested the different participants through this nice interface. So you just need your web browser for that, and you can go navigate through those scenarios. And hopefully, you know, we will this will help to build this kind of new community between smart grids and AI researchers, so that at the end we all work towards this goal of sustainability. Thanks also to smart grids. And if you want to know more about that, just check out our website, l2rpn.challenge.org, and there is a lot of stuff over there for you to read, or some videos to watch about the winning solutions. So yeah, definitely check that out. Thank you for your attention, and if you have any question, feel free.
Awesome. Thank you so much, Antoine. Yeah, folks in the audience, please feel free to keep posting questions in the Zoom chat. But just to maybe start with one. So I guess a lot of people on the call are coming from outside the power industry and would love to, you know, work on power system problems in a way that actually gets deployed. So what advice would you give to somebody who is coming from outside the power sector but wants to make sure that they're actually doing impactful work that's deployed in practice?
I mean, you know, power systems, it's actually a heavy industry. So we're not moving very fast in the past years compared to other companies. I mean, if you look at Tesla, which is also in the energy sector, it's a totally different story. I mean, startups, I think, are a good place also to make some changes there, because we definitely need some new mindsets and some new solutions. And then also try to work as a community. So that's why we try to open source and launch some challenges so that we can all work on interesting problems together and, you know, move forward. Because in the power system community, we've seen more like silos and isolated research teams sometimes, because once you publish a paper, it's not always easy to reproduce the results and everything. So I think if you try to contribute to that as well, so that everyone can participate and contribute over a similar framework, over similar data sets to benchmark solutions and to make progress, it will definitely help. But basically be open.
Awesome. So yeah, lots of different routes I'm hearing: startups, open source projects, benchmarks, lots of things. Thank you for that. So we have one question from the audience, which is generally about transparency in these kinds of machine learning solutions. So for example, what kinds of quality assessment and human in the loop techniques are leveraged to apply machine learning techniques to sustainability?
I mean, we already on the first point, human in the loop, you know, it has not been very obvious that when we're designing all our systems and applications in the past, we're really taking into account the human interaction. So hopefully we're heading there now. We're having a lot more consideration for our operators and all the knowledge they can bring and how smart they are to handle the grid. But then also with AI, we'd like to challenge them a bit, to give them maybe some counterfactual decisions or scenarios, to kind of ask them if in any sense, some other way to manage a grid couldn't be better to get, less energy losses, to handle more renewable energies. So yeah, I think that there's really a lot to do in between the interaction of humans and machines. And that's at this interface, if we have a good explainability and good interaction, where I think we can get the best flexibility towards some sustainability management tomorrow.
Yeah, that definitely makes sense. Sort of that this interface between humans and machine learning techniques will sort of in general be necessary to make these things work. Cool. So we have another question from the audience, which I'm going to make a little more general. So the question asks about, Microsoft, for example, is one of the players that is investing in AI and microgrid. But more broadly, I mean, there are, of course, other players outside the tech sector who are investing, or outside the power sector, sorry, and from the tech sector that are investing in some of these innovations. And so in general, do you have a take on some of the products and services that are coming out of these, like some of these private players in the tech sector?
Yeah, there are different level of players. I mean, in the US, it's been sometimes that there's been some energy markets, allowing many different actors in the grid to supply energy or different services. In Europe, it's been true since the year 2000. So it's been a bit slower to take off. But I think energy markets are somehow a great way, to offer some innovations. But at the same time, you have to remember that behind there's a physical system with some criticity. So yeah, it's a balance between new actors, new solutions, and still being able to handle the dynamics behind. So you were talking about Microsoft. I mean, the biggest actor maybe among the GAFAs in the energy is Google today. It's the biggest energy producer in California. And somehow they want to have this zero emission kind of consumption for the data center and everything. So things they have rather a goal at the level of the company rather than for the power grid and energy production. But it's still very interesting to see this new kind of incentives that are somehow at some point impacting the grid, and we have to coordinate. So yeah, it's an interesting time, I would say, for many
it's
actors,
definitely a super complex systems of systems kind of problem for sure. Do you have time for one last question before you have to head off?
Yeah, sure.
Awesome, thank you. So we have one last audience question, which is around reinforcement learning. So are heuristic methods along with reinforcement learning robust enough to run power networks? If somebody made a redispatch condition for a particular system, would it potentially run for other systems without changing?
I think we're still at the premises of using reinforcement learning on real systems. Even, for autonomous vehicle, we don't see for now a lot of reinforcement learning usage to build the new autonomous vehicles. So I think it's definitely worthwhile to develop at least the virtual framework in which we are trying to simulate or emulate some agents to trying to learn good behaviors, because beside reinforcement learning, it gives us a very good framework to test everything. But yeah, I mean, for using AI and reinforcement learning, you have to be also strong on your foundations, basically, your technical stack. And I know in utilities, we're not yet ready, really, to use our historical data sets, basically. So it's not we didn't have the culture to think, okay, this whole data set over 5 years, we'll use that to learn a model that will imitate some decisions and will learn some good behaviors. So we have to make this step of digitalization, and we have to label our data to have a good quality data over many years. So that's something that is starting to be in the process, but that takes time. And if we don't have that, I mean, it doesn't make sense a lot to use reinforcement learning, which is kind of the skyrocket thing we'd like to do at some point.
Awesome. Thank you so much for that super exciting talk. And yeah, for those in the audience, definitely check out this Learn to Run a Power Network challenge. It's pretty cool and sort of one of these very necessary things that where power system operators are starting to put out benchmarks and ways in which we can figure out whether some of these innovations will indeed work for power grids. So thank you so much for doing that as well, Antoine. And yeah.
Yeah, thank you very much, Priya, for organizing a very interesting webinar.
Awesome. So we're now going to move on to our next speaker, which is Dr. Kyri Baker. Kyri, are you able to share your screen?
Yes, let me do that. All right, does that look good?
Yeah, and I'm just gonna introduce you for a second and let you go on. So Dr. Kyri Baker received her BS, MS, and PhD in electrical and computer engineering from Carnegie Mellon University in 2009, 2010, and 2014, respectively. From 2015 to 2017, she worked at the National Renewable Energy Lab. And since fall 2017, she's been an assistant professor at the University of Colorado Boulder. Dr. Baker is a fellow of the Renewable and Sustainable Energy Institute, and her research focuses on renewable energy integration by changing the way the electric power grid operates. In particular, she develops computationally efficient optimization and learning algorithms for energy systems, ranging from building level assets to transmission grids. So thanks so much for joining us, Kyri, and please take it away.
Thank you, Priya. I'm very happy to be here. As you could probably tell from my background, I'm more of a traditional power systems optimization person that has now moved into ML, just because I've found it so impactful in revolutionizing the way that these systems operate. So just to give some background, how do we currently operate the grid? So the basis of operating the grid can be thought of as solving this large scale optimization problem, where the goal is generally to minimize the cost to deliver power to consumers. Now, this is just a general form right here. Inside of these constraints, we have the physical grid constraints. So how does power flow out through the network? The generation limits, various reliability constraints might be embedded in there. And this is what every grid operator generally solves to decide what power plant should be on, what power plant should be producing energy, how much energy should they be producing. This problem, the purest form of this problem, is extremely hard to solve on a very fast time scale. It's large scale. It might be over hundreds of thousands of buses, meaning nodes in the power network. It's non-convex. It has highly nonlinear constraints. It might have integer variables. Very, very challenging for us to solve this in anything more than like a 5-minute or 15-minute scale. So instead of solving this true problem, which is called the AC optimal power flow problem, grid operators traditionally do something like they'll simplify these constraints. They'll linearize them. They'll make heuristics that allow us to solve this faster and get us generally closer to something that's efficient and something that can adhere to these physical constraints. So this has been going on for a very long time. Decades, we've been solving this linearized heuristic version of this problem to operate our biggest systems, biggest physical systems in our country. So what's wrong with this? Well, what's wrong is billions of dollars annually are lost due to suboptimalities. When we're operating the grid based on something that's approximating how much it costs to deliver power somewhere, or approximating how much current can flow in that line, we're going to obviously get some losses. And you see this in some areas like ERCOT, which is the Texas power grid. Sometimes there's these huge price spikes that are partially due to environmental conditions like heat waves, but also partially due to how they operated the grid. And this was a very interesting study. This is globally, but it's estimated that about 500 million metric tons of carbon dioxide could be cut if we improve global grid efficiencies. Now, there's going to be natural losses with the power grid that are unavoidable just by sending power down a line. But by operating them more efficiently, getting rid of those losses, minimizing these inefficiencies, we can save a lot on not only dollars, but also carbon emissions. So people don't normally think about this big problem, but it's such a key part of integrating renewable energy. So what is the path forward? So there are hundreds and thousands of papers about how to solve this problem, the AC optimal power flow problem. It's a known problem that it's slow to solve it, that grid operators traditionally make all these simplifications. So these papers are generally making more linearizations that are accurate. They're breaking it up into distributed approaches where they can solve it in chunks. But maybe instead of developing a new optimization method, we can do something a little bit different. And I'm getting to my point in a second. So who cares about this? Well, if we solve the actual ACOPF problem, we can better accommodate fast fluctuating intermittent renewable sources. We can't afford to solve this on 15 minutes anymore and just rely on heuristics in between. Renewable energy fluctuations are way faster than 15 minutes. People are installing electric vehicles. They're changing the way that they operate their homes. There's smart thermostats, there's new loads, there's distributed generation. The grid is going to struggle. And we are seeing this already with the lack of infrastructure, power plants aging. There's been a ton of blackouts in California this year, for instance, not just due to it being 2020, but due to it being the power network aging. And it's going to continue to get worse. So we can also avoid the use of backup services. So when we're a little bit off with what the power plant should be producing, there's a lot of layers of backup that the grid provides to make sure that we still have reliable power at 60 hertz. And so some of those backups are like gas peaker plants. Some of those backups are called ancillary services, where the generators have these heuristic control rules they follow to adjust their output to make sure everything's stable. But we also have to look at reliability and pricing. So this is $1 billion market, electricity markets. There's many electricity markets throughout the US. If you're interested, they'll have a slightly different way of solving this ACOPF problem. But if we solve the actual problem, then people are actually getting paid what they should have gotten paid to some extent. And we can improve reliability. So let's try to solve this real problem on a time scale that's fast enough for real-time operation. So the key part of my talk and where the machine learning comes in is, can we just avoid solving this problem? Can we obtain the optimal generation values without actually solving the ACOPF problem? The way that we solve ACOPF, it's been done similarly for the past 50 years, is we obtain an initial guess, because generally we're going to use some kind of iterative optimization solver that needs an additional initial guess. We might solve a linearized version to get this initial guess. We might just start it with all ones and all zeros. We solve it, we send it to some commercial solver, or we develop our own optimization solver. Maybe it converges, maybe it doesn't converge, but inside this solve block, we have to do a bunch of things. We're generally going to have to do some kind of matrix factorizations or invert large matrices, iterate for a while, tune some parameters. It's very time consuming and not always is going to converge, which is why grid operators linearize it. But what's important to notice here is that we solve these operational optimization problems potentially hundreds of times a day for years, hundreds of times every single day for weeks, for months, for years, and we're not really using that data. Grid operators use it to develop insights, they use it for planning, but could we actually use it to speed up solving this problem? And so the proposed machine learning boosted solution, as I call it, is that we train a model offline. We have the model of the power grid, the transmission network. We can run as many ACOPFs with different scenarios as we want offline. Let's use that data. Then when we have this model, and in the work I'm going to show you today, it's a neural network, but you could use other things. I've also used a random forest, and that seemed to work decently well. When the loading in the system changes, so as people go throughout the day, they consume different levels of electricity. You just put this as a new input into the ML model, and it spits out the candidate optimal solution. This is much, much faster than solving this large scale non-convex optimization problem. Now, there's obviously issues. You're not going to always satisfy these non-convex constraints with exact precision as you would if you used an optimization solver. But as we know right now, grid operators don't satisfy those non-convex solutions either. They use linear models. Okay, I'm going to get a little bit in the weeds. Apologies if you're not an optimization person, but you've probably heard of or maybe learned in your calculus class about this optimization method called Newton-Raphson or Newton's method. It's one of the most basic methods to solve an optimization problem. And basically we start with some initial point, let's say x0. We decide what direction to move in to pursue the optimal solution of this problem while adhering to these constraints. And so all you need to know is that it's an iterative method. It, in its purest form, involves an inverse of a large matrix. It involves a bunch of matrix multiplications, which is fine. But this matrix inverse is sometimes really, really hard to do. And there's situations in the power systems universe where the inverse is actually impossible. So the matrix won't be invertible at the optimal solution. So this takes a long time. The inversion of the matrix takes a long time. There's heuristics to approximate it. But let's just not deal with this. I don't have time for this. The grid doesn't have time for this. We need to start solving this problem on a seconds level to really optimize the grid under high renewable penetration. So what I propose is that instead of performing this Newton step, which is what is at the core and the heart of a lot of optimal power flow software, is instead we replace this update with a learned Newton step. So it's going to be an iterative method. It's just we're replacing the inverse of the Jacobian multiplied by this vector of optimality conditions with an estimate of this quantity. And so what we do is we input the current loading in the network. We input our current candidate solution. We pass it through this neural network, and it spits out what the next iterate should be, or its prediction of the next iterate. So there's a lot of methods like this in the literature. Well, not a lot, but it's becoming more and more popular where people just go from inputs, meaning loads, directly to optimal solution of the non-convex ACOPF problem. I was thinking about this, and I have papers on that as well. And I was thinking that's kind of hard, going from input directly to solution. Maybe it's a little bit easier to instead learn the steps in which we iterate. And so the method or the recurrent neural network, which is barely a recurrent neural network, but it does use this output as the input to the input layer, iterates until the changes between xk and xk plus 1 are small. And learning these steps is a lot easier than learning the whole solution of the non-convex problem. Okay, so both of these are what's called fixed point iterations, meaning you can write the next iteration as a function of the previous iteration. But the key point here is that the learning-based method has an easier to evaluate F. So with somebody's question to Antoine in the previous talk, they asked, what's the bar for entry for these methods to be actually implemented in the power sector? And my theory is that we should make that bar to entry as small and as low as possible. So using something that they already use, Newton-Raphson, using an iterative method, just slightly changing the algorithm so it can be plugged and played into these power system software might be easier for these grid operators to implement. And then just a quick note for the nerds here. One really great method, or one really great aspect about this method is if you design the activation functions and the weights in a certain way, you can guarantee that the learning-based method converges. So that basically means that unlike real Newton-Raphson, which might diverge or might result in a Jacobian singularity, you can actually ensure that whatever x of k you're putting in here will converge, and thus the time to convergence is much more predictable. So you can solve this OPF, this approximate OPF problem in regular time intervals. Okay, how well does it perform? So this was just a first pass, one hidden layer, not a huge network. I just tried to see how well it would perform. So here's a here's a IEEE 30 bus system, which is one of the typical power system test cases. The optimal solution for these generators is shown as the black dashed line, and what the neural network predicted is shown as the colored line. So you can see that it's extremely close to the true optimal, and it only takes about a second to get these optimal solutions, which is very, very fast. Now, if you were to plot what the grid operators use now, it would actually be even, and I should have done that, it would have be even farther from the true optimal. So the linearizations they're using now are even worse than what the neural network is predicting. So what was the error across the testing data set I used? So I went all the way up to a 1300 bus set. So the error from the true cost, which again is generally even higher under these linear models, in the worst case, the average error is around 1%. So that's not bad. Now the active power is a little bit, the error in active power, which is, yeah, I guess I don't have time to explain active power and reactive power, but generally the amount of power that these power plants are generating wasn't, there's still some error here, obviously, as there is with the linear models that neglect losses, which is what the grid operators use. But, we're getting there. And this is a first pass to see what's the potential of a method like this. And this allows us to do real-time solution tracking. So let's assume that we want to balance out load fluctuations that are on a 1 second level. This black dashed line, so here's just 30 seconds of somebody consuming power, is the true AC optimal power flow solution. If we had infinite computing power and we were able to actually solve this problem in 1 second, that's the black dashed line. Now, I used a commercial solver specifically tuned to solve AC optimal power flow problems, MAP power. MAP power on average takes a couple seconds to solve this. It's still a fast solver. But because it takes a couple seconds to solve every single OPF problem, it has a lag between when it's providing optimal solutions to the generators. So you can see this lag where it gets the load value, it solves the OPF problem, sends those values to the generators. It's already out of date. Those optimal generation values are already out of date. So the learning boosted solution solves extremely quickly, like 1 second or less than 1 second for every single point it gets. It's approximate, obviously. You can see that it has some errors. And this is generally what, when I submit papers on this topic, people complain about is that there's errors, but of course there's errors. It's another approximation of the ACOPF problem. But generally it tracks this solution much faster with much lower delay. Okay. So I want to be respectful of my time limit. So thank you. This work was also performed with some of the members of my lab, which is called the Griffin Lab at CU Boulder. If you're interested in some of our other stuff, I encourage you to check out our lab's webpage. And I'd be happy to take any questions.
Awesome. Thank you so much, Kyri. So I'm going to give one question now, sort of as we transition to the next speaker, which is Eric. So Eric, feel free to also share your screen. But I guess there is one kind of more macro scale question in general, which is that this work focused on machine learning for speeding up, centralized optimization problems. And so the sort of devil's advocate question was, do we need machine learning for grid management or dispatch, or do we need to more intelligently design, market-based protocols with more layered system designs? And is like that a better direction in general to be going in?
Well, I think the key part here is that we just need to solve this problem faster. We also need to totally revise how the markets work. We need to revise the models in which the markets operate. And also, I have a lot of stuff to say about other things in this area, but the key point is just, let's not solve this large scale optimization problem. There's no way we're gonna do it unless we just wait around for computing power to increase. So let's figure out how we can use that historical data to speed this process up that we do multiple times a day.
Awesome. Thank you. And you'll see there are a couple of questions in the chat that are coming that are specific to you. So feel free to, if you want, respond in the chat to some of those. And then we'll also get to some of the more general ones at the end. So thanks so much.
Thank you.
And so next is Eric Xie, who is the head of product for AI and ML applications for AutoGrid, an energy industry software company. Previously, Eric worked as a senior machine learning engineer for AutoGrid, where he built and deployed a predictive maintenance model at a Fortune 500 energy company that catches distribution outages with IoT data in real time. Now, as the head of product, Eric aims to make the energy grid more efficient by productizing AI applications. He received his formal education in evolutionary biology from the University of Michigan at Ann Arbor, where he founded a biofuel startup that made energy from brewery wastewater. In his free time, Eric enjoys gardening and golfing. So again, thanks so much, Eric, for joining us, and take it away.
Hi, can everybody hear me fine?
Yes,
cool.
We can hear you.
So actually, Priya, and now how much time do I have? 15 minutes?
Yes.
Okay, got it. All right, good morning, everyone. And I love this virtual format. Talking to 400 people on a virtual format is less intimidating than in person. All right, so I'll dive right into it since we have short time. So today I'll be talking about actually productizing and making and presenting to you guys a machine learning model that actually run at one of the utility in the US, a large scale utility, specifically focusing on the distribution. Oops. Okay, so just to give you like a very brief background about AutoGrid, where I'm currently working at. We're a machine learning company for the energy grid. We're a startup here in the Silicon Valley, about $80 million in funding, and we had our customers are Fortune 500 energy company, usually utilities. We have partners like E.ON, CLP, Envision, Total, and other big players. So that's just kind of who we are. I think the company was started here it is, 2011. Yeah, right out of Stanford. The founder was actually a director of the Smart Grid institution in Stanford. This is a very brief background on AutoGrid. So actually, before jumping in, the applications that we have, right, focus on just making machine learning software for energy grid. So sometimes it is like flexibility management, storage optimization for the battery, and demand responses. Today, I will specifically focus on the outage problem in our company. So I don't have a slide on this, but outage is a very big problem in the utility. And just looking at the distribution, it's about a $100 billion like total loss to the economy based on like the utility, the businesses, the people. Think about all the time that you're out. So like the actual outages is about it costs about $100 billion worth of loss, right? And currently, the industry solution, it's two things, right? From a more primitive perspective. Usually, sometimes we don't even do anything until the outage happened and we go fix it. Another times that when we want to do something, usually it's based on physical models. Sorry, so these are like, hey, if I see signal A and B and C, I know something is going to fail. And using the physics, that's like kind of like the rule model we're going to implement. Right? As you can see, there's very many different type of outages. They all have different patterns, and using those kind of like physical models can be kind of hard to catch up. And also there are just, for every single equipment, you need to kind of have a different model. So because of that, it's not very optimal, right? So it's a big problem. A lot of people are having outages. We're very reactive towards it. And our solution are basically just equations, right? A lot of equations, or none of them actually, so a lot of times. So there has been an IoT revolution on the distribution grid for the past, I would say like a little bit less than a decade, right? We're starting to put all these IoT devices across the entire distribution, right? So in the substation, which is, I don't know if everybody knows how distribution works, right? So basically you have power being generated at a source and then being sent at what we call a substation, and then that substation, right, then distributed energy across entire regions. So our story starts with after the power generation reaches a substation. So think about that as like a highway, right? A start of a highway. And then you kind of have like all these things that we call feeder lines that go across a state or region, right? So these tiny highways will then like send your electricity across your home, and et cetera, et cetera. So these, at any given of these point, right, when things fail, you take down a community, you take down a business, right? So we've been installing a bunch of IoT devices on every sector of these grids. So we have things at the substation, things at the very end, we have smart meters that aim to just monitor while everything is going on. So think about it as like just slapping on a bunch of Apple Watches on the distribution grid and just seeing like how things are being reactive. Right. So we have a lot of explosion of the data, actually 3,000 times data than we had before. But right now, those data, we're just kind of like saving it, right? Because we need historical data to make any meaningful prediction. and they're underutilized. We're not doing anything. So utilities are spending like millions and billions of dollars on installing these devices, but we're just not using anything to the full potential. One of the use cases is using this for outage prediction. Right? That's not what it's only designed for, but it can be used as that. Right? So, this is hard to operate. Okay, so currently in any big utility, there's kind of two teams to do outage management. One is the operation team. So these are kind of like after an outage happened, right? Have you guys all experienced that you got a phone call and like, hey, by the way, the power's off, like it is unplanned. And a bunch of guys were like move in with trucks and try to fix things and try to restore things, right? So these are like the post-outage team, right? So these are your outage team within utilities. There's also the maintenance team, which is basically responsible of, hey, what is the maintenance schedule like for entire distribution grid, right? And what do we need to do? What type of thing we need to install? What thing we need to inspect? So these are trying to catch it before it happens. Right? But if you think about it, they're kind of the same thing. Right? The operation team basically try to fix stuff after it happened. The maintenance team try to fix stuff before it happened. But theoretically, if we know if something is going to happen, if we can fix it before, then operation and maintenance can merge into one thing. So before of that, that's kind of impossible. We get a big question as well. The outage didn't happen. How do we know that there will be an outage? Right? So with the help of data, right, and then with the help of machine learning, what we have figured out basically is that utility is one of the rare industry that has really, so what we call target data in machine learning, right? We need these targets. So sometimes you're like, oh yeah, we can train a machine learning model because we don't really have something to train against. Right? So most of the industry don't have a label, right? You need to hand label it yourself. Well, utility industry, well, we're very blessed because all these outages has happened, right? We're required by the law to keep a close record of exactly when an outage happened, how big it was, where it was, et cetera, et cetera. And so now the story basically goes, the IoT data devices becomes our input data and the outage record becomes our target. And if we can match those two, then we can basically, for the future, figure out when it's going to happen before it actually happens. Right? And the more excitingly for this specific method, it allows us to kind of focus on the type of outages that we want to focus on, right? So as you guys can tell, like there's a lot of type of outages that you can't really predict. Like for example, someone drive down the road and hit a pole and the pole fell. Like you can't just predict someone's going to drunk drive and hit into a pole, or that's just impossible, right? But if something is caused by an equipment, that means that is the thing that we can focus on. Also, as I was telling you guys about the distribution network, there's different, like not all outages are equal, right? Sometimes an outage will take down the entire Bay Area. Actually, that never happens. A sector of the Bay Area. Sometimes it would just take down 5 houses, right? But if you use a physical model, it can look very similar, right? Something that takes down the 5 houses, like it's just happened, like which junction of the grid did it take down? But if we have label record, we basically know the scale. So we can basically say that, hey, by the way, if this is like a traffic jam problem, I only want to predict a very bad traffic jam if it's on a 101. If it's on like the road outside my house, I don't care about that. Right? So it allows us to laser in on the outages, which is actually only 2% of the total outages, but it's responsible for 50% of the economic loss for the utility, and it allows us to laser in on that. And that's what we have applied what to do. So this is as technical as I'm going to go. But basically, this is the machine learning overview at a 3,000 feet level, right? And I'm happy to answer more questions. But basically, there is 2 modes. There is a historical mode, and then there's a live mode. Right? So in the historical mode, we're talking about taking all these years of IoT data that we've kept in record, right, that we've been storing by the utilities, and taking all these years of data that we have the outage record, and basically matching that. So the input, right, the features here are your IoT time series, right? So like voltage, faults, breaker operation, stuff like that. Your health record, the manufacturing background, the hardening schedule, et cetera, whether it's close to the ocean. So all these input, right, using as things that we will predict. The output here are the maintenance record, right? These things have been actually even longer history than this. So hey, exactly when outage will happen, what type of outage is equipment, there's squirrel, bite a cable, causing an outage to go down. Was it a balloon? Actually, I saw one of the Costco one time was an airplane. I don't know exactly what airplane outage is. So let's presume, yeah. So all these things in machine learning, we match the record, right? And then we train a machine learning model. What we call a backcasting to basically like, hey, if I would have deployed this model tomorrow, how good this will be. And then once we get a good model, we deploy it into production, right? So then utility actually send us these IoT data in real time, run through the machine learning models, and then we send out alerts to the operators. So let me just give you guys a glimpse how that will look like. For example, on Monday, you have one of the IoT signals that says, hey, current spike, right? And then run through the machine learning model. Machine learning model says, yeah, I've seen worse before. I think we're not getting to alarm. Okay. On Thursday, we got more stuff, right? Some fault, some breaker operations. So machine learning models will be like, yeah, it's bad. It's worse than before, but I've seen worse, right? Based on my 6 and 10 years of historical record, I've seen worse. Some high voltage happened again later that evening. And the machine learning models will say that, well, that according to my, my past record, this is pretty bad, but it is not as bad. I'm going to scream. Then some AMI, last gas, which is like basically the meter start disconnecting from the system. The machine learning model, run the match and see the pattern and be like, you know what, this is pretty bad. Okay, I run my past record, or this is a very bad student. I'm going to send a warning to the parents. So poof, it sent out an alert. And then the operator actually got this in real time. And then just say, oh, we need to go inspect this and this and this location and fix these stuff before it fails. Right? That's just kind of like give you guys an idea about how it looks like. Right? So now the actual, the whole workflow is more complicated than this. You have the machine learning model, it generates alerts. And once it generates alerts, actually we dispatch a drone, right, that go inspect. And Caitlin and Vic will talk more about drones and their amazing startup of drone inspection. And basically the drone will go out there, inspect the images. If they see a high heat event, it will come back and the operator will actually go and inspect it, right? So actually drone and AI on the branch level will allow us to kind of laser focus in on the outage further. All right. Oh, I'm pretty good on time. All right, so I'm just gonna conclude with some of the business impact and just kind of like a summary of what this has done. Right? So we actually have deployed a system at a major U.S. utility, and we're scaling into more of them for since 2017 and way before that. So this is kind of like the most current model, right? So for this span of time, we have about 15 million of customer minutes of interrupted. So those are basically like a metric of how many customer lose and power based on the minute. So there's about 15 million minutes, right? And they will run about 91% field precision. Now that number is pretty impressive. Well, but like kind of treat that number as field like vaccine immunity, right? 94% things in the lab, that kind of stuff. So that number is going to fluctuate. But the more of a story is that at 91%, we're pretty much confident that the alerts that we're predicting are statistical significance, right? That when we send out these crew out to inspect something, we're not just sending them out to middle of nowhere and fixing nothing, right? And that's and that kind of concludes my presentation. And I'll hand it off to Priya and Na.
All right, thanks so much, Eric. So I'm going to ask sort of one audience question as we transition over to the Buzz Solutions team. So Caitlin, if you'd be willing to share your screen in the meantime. One question that came up was, has the installed base of IoT been able to track the dynamic behavior and impact in distribution grids that have more than, like, let's say, a 35% rooftop solar penetration rate, so really large rooftop solar penetration rates?
Rooftop. So you're talking about solar here?
So like, have you basically, I think the question is getting at how do your solutions generalize to these, distribution grids that do have very, very large renewable penetration when you're thinking of the prediction?
Oh, I see. Yeah. So, I mean, any machine learning problem, right? We always start with the phrase, it depends. So it depends. I think it really depends on like whether or not your record has matched, right? So like, for example, if you have 3 years of historical record and that record has renewable data in them, then yes, I think it will be matching pretty well. If the grid has constantly changing, that means that you need to retrain your model pretty often to make sure that the population data matches the sample data set. So far, in terms of the renewable penetration rate for the region that we're looking at, it hasn't been a problem. But in the future, we expect that as more renewable devices get installed, the distribution of the data will change. But that for machine learning, all that means is just click a button, readjust the training. I mean, making it sound easy, but it's hard. But you're just changing the time frame that you're training at. And I think the key thing here is that you want to make sure that whatever data you're trained matches this real world that you're looking at, right? So if this real world is looking very different, so my advice would be maybe wait a year or two to get the right type of historical data set before deploying your model. Sounds good?
Awesome. Thank you. And there are a couple of additional questions coming in the chat. So if you are willing, feel free to also answer some of these additional ones in there.
No problem. I'll go do my homework while you guys are.
Sounds good. And so our last speakers today are Caitlin Albertoli and Vic Chowdhury from Buzz Solutions. So Caitlin and Vic met during their time at Stanford University and created Buzz Solutions from a Launchpad course there in the spring of 2017. Together, they bring a well-rounded and complementary skill set to the table. So Vic has a master's degree in energy engineering from Stanford, focusing on applications of machine learning and AI for smart grid technologies, demand response, and energy efficiency. And he also has several years of experience with AI and machine learning and computer vision, leading ML teams at Cisco Systems. Caitlin also graduated from Stanford with coursework in economics and finance, and she has previous experience working in finance at JP Morgan. She also ran a nonprofit in the sustainable food space. So together, they're very passionate about bringing the digital transformation to a traditional industry with a burning need to modernize the aging grid infrastructure and to put an end to some of the mass disasters such as wildfires, forced shutdowns, and network failures as a result of failed infrastructure. So Caitlin and Vic, thanks again so much for joining us. And yeah, take it away.
Great, thank you so much, Priya. Really appreciate it. So we are Buzz Solutions, and we are safeguarding the world's energy infrastructure by providing actionable insights and predictive analytics for grid inspections. Vic, if you wanted to give a little bit about your background. Can you hear us? Oh, Vic, you're on mute.
Okay, sorry, I was not able to unmute myself. The host had to, so sorry about that. Hey everyone, I'm Vic Chowdhury with Caitlin. We are the two co-founders. So about my background, I'm also the CTO and COO at Buzz, graduated from Stanford University, have a deep background in energy systems and then application of data science, ML, AI technologies to that field. And we met at Stanford in spring of 2017, and that's where we started Buzz from, where we stumbled upon this burning need of power line inspections. So one of the projects I was working at Stanford with my master's degree advisor was leveraging drones to optimize wind turbines and inspect them. So we were developing technologies, we were developing models to optimize and inspect wind turbines, and wanted to apply that technology to the power sector where it was a bigger need. And that's where we met and discussed this idea. Caitlin?
Yeah, absolutely. And so that's where I also got involved in the energy space after my experience in the sustainability space. And since 2017, we've continued to grow Buzz Solutions. We're also backed by a very strong team of advisors with industry experience. And yeah, just a little bit more about Buzz, where we are today. So we're a seed funded company and we are a team of 6, but we're actively growing. We launched in 2017 and had a commercially deployable product in August of 2019. We've also worked with several utilities with our solution and have validated our technology working with EPRI, the Electric Power Research Institute, as well as several utilities to deploy our solution. And so just to talk a little bit more about the problem and where we fit into this. So utilities are mandated to inspect all of their transmission and distribution infrastructure, and they do so visually using helicopters, drones, fixed wing aircraft, linemen capturing images, walking underneath the line. And now they're capturing hundreds of thousands and millions of images on an annual basis. We were actually quoted that in 2020, one large utility in California is planning to capture 10 to 20 million images using multiple drone service providers and helicopter providers. But the process on the back end of actually analyzing all of this data is entirely manual. They have teams of hundreds of linemen and engineers who are manually stitching together all of this data and looking for any visible faults that they can see compared to a list of different failure modes that they have. It's taking about 6 to 8 months per inspection cycle. And as a result, the sector is losing about $170 billion due to network failures, forced shutdowns, and mass disasters such as wildfires, which have become an increasing problem in California. And so that's where we see that there's a huge need in this industry.
And that's where we are coming in. So our vision is to provide a digital transformation for the utility sector. As you know, our infrastructure is aging, and with more climate change effects and consequences affecting the grid, we are seeing patterns of heat waves, we are seeing patterns of droughts in other places in US. There is a lot of strain happening, and with much more renewables getting added to the system, on the grid, there is strain happening on the grid, and that causes a lot of aging of the infrastructure quickly. And that is our solution. So since there's a lot of data being captured in the field and all that data is being brought back to the utility, the process on the back end is still manual. And that's where we're plugging in with our AI systems to provide a real-time processing capability to process all that visual data that is being captured in the field and save months of time of this manual analysis, during which a power line can go down, or a forced network shutdown can happen, or even in extreme conditions, a wildfire can start. Secondly, we are also automating that whole process. So we're detecting all the major anomalies or faults that are happening on electrical components, on transmission and distribution networks. And we are doing that with the highest degree of accuracy right now with our models. We are also saving utilities on an average 50% on costs as compared to what they were doing manually by processing all that manual data or manual visual images that they're capturing. So we're providing them a much more automated approach on the back end for that. And lastly, we are also providing analytics, and we are going towards a predictive solution. And as Eric highlighted a little bit on the predictive capabilities, we are helping utilities to capture all that historical data and our models and our machine learning models to see all these historical patterns and overlay them with various other kind of data sources, such as weather, climate data, smart meter data, all those kind of data sources, and build a predictive asset management system that can help utilities save much more on outage prediction. So we estimated that utilities can save an additional $3 to $6 million annually by outage prediction, that capabilities that we can provide to them. So just to talk a little bit more about what we are providing to our end customers. So what they see is a software platform, which is a one-stop shop where they can upload or manage their data, all that visual data that is being captured by drones, helicopters, fixed-wing aircraft in one place. And then they can process all that data in one place using our computer vision, machine vision models, which are proprietary to us. And after that, the models, when they have done processing on this data, they flag instances for different kind of faults or failure modes on these assets, electrical components, whether it be insulators, conductors, damages to them. As you can see over here, there's an example of a flashover on the insulator, and that is being plotted on a geomap also, so that the utilities and our end customers can see where these kind of problems are happening and can kind of nail down on regions which are hotspot regions and can take mitigation actions on top of that. Just to talk more about the AI capability, again, our asset fault detection AI is very proprietary to us. We have built this system from scratch. Given that off-the-shelf kind of computer vision models don't really work in this space, we have tried those just because the data being captured is so variable. It's coming from different camera sensors, from different kind of drones, coming from helicopters, from fixed-wing aircraft. So we see a lot of variability. We see a lot of signal to noise. We see a lot of background noise in this use case on the data. So what we are providing is a holistic system that can take in data from multiple sources, and the machine vision or the computer vision models that we have built can detect all, first of all, different kind of assets on these on the lines, on the transmission distribution lines, but also going beyond is detecting different kind of failure modes or anomalies on these assets. So for example, as you can see over here, there's dampers that are damaged. Clearly, they're broken insulators, and assigning severity metrics to them with the highest degree of precision. On an average, we hit 95% precision on our predictions. And in certain recent cases, we have also hit 99% on our precision with some of the pilots that we have ran with major utilities and their in-field data. So as you can see over here, there are a lot of problems that are happening on components out in the field, the physical components, and there needs to be a system that can detect that and take actions on that. And this is what we are plugging in and providing to the utilities. So going beyond processing and AI-based detection, we also provide on top of that analytics. So the utilities or our end customers also get an analytical solution. They get all the results in one place where the line, the feeder line or transmission corridor is mapped on a geomap, as you can see over here, and all the structures and assets are mapped on that. And what you can see is different kind of places where the problems are happening and the detections are done so that they can be plotted and be visualized in one central location. And you can see how different kind of elements come together, how different kind of multiple images captured around structures come together to map to one structure and then to a feeder line, and that can be helpful to operational people who are doing inspections and maintenance to go out in the field and provide mitigation strategies over there, either repair or replace. So insights and analytics are very helpful to utilities because they can see in one place where the problems are happening and what they can do with that. This is another part of our analytics capabilities. Again, different kind of visualizations are displayed on our analytics dashboards in our platform, but also we capture the time series element of that. So that feeds to our predictive capabilities, which I'll talk more in the next slide. So as we're talking about, a predictive asset management system is a system that we are building, and we're working with Eric's team over there too. As Eric highlighted, this is a major value add for utilities going ahead, in which detection is one piece, but going ahead is predicting and prescripting what can happen in the future and forecasting the health of the line or health of the assets that are deployed in the field. So basically we take historical data sets, visual data sets, and see patterns in those data sets. We overlay them with different kind of data sources, whether it be climatic conditions, weather data, humidity, temperature, wind speeds, because they affect physical infrastructure a lot. Take historical patterns of those, and also overlay with line data. So the kind of SCADA data, line data, meter data that is coming in real time and historically time series data, and feed that into one engine that can predict or forecast the health of the line going ahead. So that system can basically forecast if a line has, for example, 6 months down the line, there is going to be, historically, we have seen in this region, we have seen 10 insulators being damaged. So statistically, we are saying that there's an 85% likelihood that there might be 8 insulators that can go down, because historically we have seen those patterns. Our machines have seen those patterns. So that is a big value add, because that helps utilities to kind of have a guided approach of addressing the solution of inspection and maintenance rather than shooting in the dark. And this kind of takes a sector from being reactive to the problems to being more proactive and predictive in its approach, something that Eric highlighted in his slide deck also.
So looking at the market opportunity for this, so internationally, it's a $165 billion market just for analytics. But as the grid continues to age and as mandates become more strict on utilities, it's causing a massive increase in data. Several of the utilities that we're working with now have seen a 10x increase in data over the past few years and are continuing to build out these large in-house drone teams. So these in-house drone teams are working around the clock to conduct all of these inspections and are flying the lines on both the transmission and distribution infrastructure, as we're looking at autonomous drone capabilities and beyond visual line of sight regulations, allowing for complete autonomous drone inspections. This amount of data will continue to increase. Internationally, the market's actually expected to double by 2030 as well. And that's particularly with regards to these increased inspections. And so that's where, you know, our biggest value add is, as this amount of data continues to increase, we can provide more and more direct cost savings. And that's where machine learning and AI just is going to take over this field, because it's not possible to conduct these analytics processes and this visual data processing manually anymore. As this data becomes greater and greater, the need for fault detection and also for predictive capabilities becomes even more significant. And that's where we're saving about 6 to 8 months of inspection and analysis time, and then that $3 to $6 million per utility working with our predictive asset management system as well. So that's what we're working on right now at Buzz Solutions. Thanks so much for the time.
Thank you. We'll take any questions, Fred.
Awesome. Thanks so much, you both. So we're actually going to transition into the general panel portion of this. We have just a couple of minutes for it, if that's fine. And I guess we have a couple of questions coming in from the audience, and please feel free to keep posting questions, everybody. The questions so far have been great. Thank you. But to maybe start with one higher level one for everybody. In general, what advice would you give to someone who's just getting started working at this intersection of climate change, machine learning, and power systems about how they can be sure to do, you know, well-informed and impactful work? And sort of on the flip side, for those who already are working in this area, are there common mistakes or misconceptions or pitfalls that you see that they should try to avoid? So anybody feel free to jump in.
Sure, I can give some thoughts on this. So I will say that it's energy and machine learning, right? And I think depends on where you want to focus is. If your focus is more on the technical side, I will say that the things in bold will probably be in machine learning, right? So the things used in energy industry is basically it's very similar to the rest of the industry. So definitely like sharpening up your data science skill, your machine learning skill, know the basic concept, and then maybe that in your practice, you can focus more on the data set that is energy related. On the business side, I think it will be doing both, right? You really have to look at the business case and the industry and how it's currently going as well.
I can follow up on that a little bit. So someone who's looking to start in the energy sector with ML AI capabilities, I think there is a huge opportunity coming ahead. There are fields like we're working in the smart grid arena. There's smart grid technologies, demand response with more DERs and even energy efficiency. Now we're seeing microgrids. So there is a lot of use cases where machine learning can be applied in that area. And specifically on the technical side, if people are interested on the deep learning aspect of that. So recurrent neural networks are, again, with energy use cases, there's a lot of time series data being captured by IoT devices. So RNNs are a perfect fit over there. We use convolutional neural networks. So that's more on the image side of things. But yeah, definitely someone who wants to get involved in this sector, machine learning has a big opportunity over here, and they can definitely leverage the technologies and the learnings from different machine learning use cases and apply that to energy use cases.
Don't forget to send your resume to him.
I think something I would follow up on as well is, we see specifically working in the power sector that it is a very traditional industry. And so I think a lot as we're transitioning towards this AI, machine learning, digital transformation, there is a huge need for education too on how to apply these use cases and exactly where machine learning can add the biggest value. And there's a lot of education that needs to happen specifically on implementation and integrations of these solutions. And so that's something that we're excited to be at the forefront of. And also, I think that over the next few years, we're going to continue to see that this, specifically in the power sector, is going to continue to grow more and become an even bigger problem that needs, education.
Yeah, and then I would just add the last thing to that is to be cognizant and respectful of the decades of experience that grid operators and people in the power industry have brought Because as we come into this, we're like, oh, I have this data, I trained the model, it has a 99.87% accuracy. But it's like, there's a lot of human intervention that Antoine was kind of talking about it. A lot of things that are done in the actual utility rooms, in those actual system operator rooms, are a lot of human in the loop. There's a lot of know-how. They used to tell power plants to turn on via phone. There's a lot of manual things that still go on, and that knowledge needs to be embedded in those ML models. It's going to be hard to do a complete overhaul of the way the grid operates now, but dealing with it in a modular piece by piece fashion might be more realistic.
Yeah, those are all really great insights. So we also have a series of questions that came in at various times about wildfires and rolling blackouts. And so I think there's a lot of curiosity to understand how each of your work potentially fits in with this question of preventing fires and other really harmful outages here.
So we can start over here on the bus side, because we have been trying to mitigate a lot of wildfire issues. Again, that has come aboard because of failed grid infrastructure. As you see in the cases of major utilities, I won't name anyone, but in the past few years, because of failed grid infrastructure, we have seen a lot of wildfires start or even spread. So that is where we are trying to plug in to provide that, again, with our technology, our solutions, to provide that capability to early detect if the grid infrastructure is going to fail. And because I'll give an example. For example, if a transformer is malfunctioning and has been degraded, there might be a sparking, and if there's vegetation growing around that, and it's dry vegetation, that can cause the start of a fire, and that can spread. That's what we have seen in California in a lot of cases. So that is where we are also trying to plug in with our solutions to detect these anomalies that are out there in the physical environment. If vegetation is growing very close to the power line, or is in proximity of the power line, or if the components are also damaged on these high transmission lines. So detecting those early on and sending out an alert to the operators, to the inspection teams, to the maintenance teams at utilities is what we are trying to do, so that we can build a preventative measure for them so that they can take action on these cases and prevent wildfires from happening. So that's our grid resiliency, and making it more stable and resilient is one of our use cases from our technology.
Yeah, I think what Vic was alluding to was the most expensive natural disaster in the history of the world, which was caused by failing infrastructure that could have been prevented if that failing infrastructure was detected. Along with the failing infrastructure, just operating subsets of grids like microgrids in more efficient ways can help prevent wildfires and detaching communities from wildfires. One of the projects we're working on right now is with a mountain utility in Colorado, and it was within 5 miles of one of the wildfires in Colorado. So, helping that community be self-sufficient with a combination of demand side resources and solar and batteries could really help provide them power until that, the power is able to be restored in those rural areas.
Yeah, and I can, I will say that, yeah, there's a lot of natural disaster and there's kind of big failures going on, but the utilities are under the scene, I think, doing a lot, and that's not public. And it really depends on the data set, right? Whether or not there's a signal. So storm, wildfire, they're working on it. We are working on it, and I think it's all part of the whole data upgrade, because as time goes on, I think it's very important that we kept the data governance good, and eventually we'll get there. And it's not like one day that we're just going to figure out predicted model, but it'll slowly get there by having better data set, more granular data set. And I think that's what most utilities are doing. And I think we're doing a better job on the storm management side than vegetation. Vegetation is a harder problem because it's more granular. Yeah, I'm pretty confident that with better data governance, we'll have better historical data, and that will produce better models. Always go back to the original data set. And I think, like Kyri said earlier, it's very important that we know that there's a lot of work that's already been done, right? So we're more like AI assist rather than AI empower. We're not trying to take away anyone's job. We're trying to use AI to make the operators more efficient. So even if the vegetation management is a little bit better. AI can help it a little bit more. That'll translate into a lot of value. And I think it's very important to do that and not say that, hey, we have this better model and it will solve everything, because it's not going to. Yeah.
Yeah, and I think to even add on to that point there is we're seeing that utilities are capturing so much more data now, and it's just figuring out how to use that data most optimally and how to actually make actionable, take action from that data. And so that's where we're working with machine learning to be that tool, that assistance to help make sense of that data, so then they can take all of that information and do faster maintenance, faster operations, and actually improve those processes. So it goes back to that exact point. We're a tool to assist, not to take over and eliminate jobs.
All right, thanks everyone. So we're unfortunately not going to get a chance to get to all the audience questions, but if you would like to, if you're in the audience and you want to continue this conversation, there are two resources that have been posted in the chat. One of which is the Climate Change AI Forum, which you can get to at forum.climatechange.ai. And the other is the Energy Innovation Network Slack community, which there's a link to in the chat as well. So please feel free to join those. And again, the goal is really here to make connections and actually get started working in these areas. So I hope that these resources can help you do that. To the panelists, do you have time to stick around for one more question? I know we're already a little over time.
Yeah,
yes,
sure.
Absolutely.
Yeah, sure.
I do.
Okay, fantastic, thank you. So I guess this last question is that a lot of innovation and work in the power sector plays out over very long time scales. So I know Caitlin and I, for example, had a conversation about sort of the amount of groundwork and the number of years it sort of took to get these solutions integrated with power system operators. Work in academia also takes a while to trickle in, and yet we obviously have to deal with many electricity system problems and climate change problems fairly quickly. And so how do you sort of think about this in your own work? How do you deal with, for example, like VC timelines being very short time scale, even though a lot of these things are long time scale? Or how do you deal with the fact that in some ways academic work does take a long time to have an impact, given this sort of urgency of acting on these problems?
I think from the academic side, that's a bit of the extreme case, because we're always, far behind in our little offices doing whatever we find interesting. So I think, when I first started in this area, I was just interested in optimization. And then as I saw the importance of it with relation to renewable energy and climate change, it really kicked me in the butt to want to make a difference. And so I think one thing you can do is just talk to utilities, talk to grid operators, say, hey, would you be willing to try this? And having that discussion has really enlightened me to what the practical issues are. It's not just these algorithmic things that I talked about today. It's actually, how do we change the software? How do we embed something existing? So just having those conversations and not being so enamored by the research part of it has been important for me.
Yeah, I can agree on that in terms of research and academia, especially in machine learning. There can be a disconnect between industry and academia sometimes. So it's very important to, that's what we did with Buzz also. We had to go out, talk to various, field technicians, linemen, operators, inspection, team members, maintenance members of utilities, and get to know their problems, and so that we can apply these kind of models in the right way. In terms of, working on projects, yes, energy projects and utility projects do take a lot of time from, starting off with a POC or demo and then going towards commercialization and full-scale deployment. Again, because there are multiple, factors and aspects that are in play, human in the loop capabilities. If you're deploying machine learning, ML kind of models, they have to be very certain in their, deployments, because again, we don't want to deploy a half solution over there, because there is a lot of liability on the lines. If something goes wrong, there is a lot of impact on society because of that. So these projects do take a lot of time, and I think going to the fact that there are long sales cycles with utilities, and VCs are generally, they want quick ROIs. So that is a conversation, you have with energy VCs and energy venture firms that know about these long sales cycle, and they want to know how you can, mitigate that or kind of tackle that with the right approach. So one of our approaches we'll give an example is using channel partnerships. So we partner with existing utility companies and channels that can help us get to the market really fast and fast track, accelerate our sales cycle. But again, the projects still take a lot of time than, the existing or conventional B2C or conventional enterprise B2B companies. But that is the point of working in the energy sector, because it does take a lot of time. But once you're in the system of utilities, the value that you add from these projects and contracts is huge.
Yeah, and I think it's very impact driven too. I think that we're tackling and trying to help these utilities solve some of these massive problems that are only continuing to increase. The power outages, forced shutdowns and wildfires are becoming, and storms, impacts from storms too, are becoming incredibly huge problems that are not just impacting the utility itself, but all the people in the surrounding areas. And so that, when you're looking at the business side of things and working with VCs and things of that nature, it's selling them on this vision of the impact that we're hoping to help provide, and the problems that we're hoping to solve. And so getting aligned with the right people there is just so important when working on these longer term type businesses that don't have the quicker payouts.
And I'll add finally that it's being on the private side helps because as businesses we have fire on their ass, bosses, making sure that we're closing contracts. So I think that framework there is very helpful in moving things, right? So making sure you're delivering value to your customers, you're hitting a deadline, that will speed things up, right? But as we don't run on the full Silicon Valley mantra, like we want to move fast and don't break things. So I think that's also very important that we test things often. We're not like any other starter that we can just fix something. It's things that you deploy are affecting actual people, pulling up poles that are high up there. So I want to make sure that we're very robust. So I think sometimes some inefficiency, it is a good thing because we're not like any other application that we can just hit a button and change the color, everyone will be happy again. It's more serious than that. And also if you made a mistake, then the whole industry kind of like, ooh, we're already skeptical about the system. Like, so I think the balance of validation and making sure that we're moving fast, I think is a delicate one. So I think on the speed part, I'm pretty confident that investors what will be the biggest pusher on the speed. And then on the robust part, right, that really is something that us scientists, right, and people on the engineering side needs to be thinking twice, because once you screw it up, it's really hard to roll back.
Okay. All right, so I think that's a wrap. So thank you so much to all the panelists. We're getting some great feedback in the chat saying that people really enjoyed it. So yeah, thanks. And again, to those in the audience, we'll keep the conversation going on the Climate Change AI Forum and the EIN Slack. So please feel free to join those and have a great day.
Thanks,
Thank you, everybody.
Thank you,
so
everyone.
much.
Thank you.
Take care. Bye.